They were closing on the house. Remember, for people who had me last semester, remember at the beginning I had a funeral I ended up having to go to? So we finally closed on the house. And the person who bought the house actually found, so he was a hoarder in general, so they actually found something in the house that we had to go pick up. And I was the only one that literally could get anywhere to go get it, and it was on the other side of the state. So I was like, it just wasn't going to happen. Come back. So, yeah, it was. It's cleaning stuff out sucked. All right, so we're gonna work. We last Tuesday we really were talking about sequences, and we were looking at convergence and divergence of sequences. Sequences are great, but most of the stuff that you're going to actually do are series and are basically summations of things. If you remember when we were doing like Riemann sums and those type of things, it was all summation problems. So calculus really wants to understand how series works as they go to infinity. Do they diverge? Do they converge? And if they converge, where do they converge to? So we need to start being able to figure this stuff out. So somebody said the next test should be pretty easy. I'm like, yes, because it's basically true and false. The vast majority of the questions are going to be, does this converge or diverge? The key part of the question, though, is not actually the answer. It's how did you get the answer? So yes, it converges, but why? So that's really going to be the questions that I'm going to be looking at more than you just guessing convergence or divergence. So we kind of talked about what convergence and divergence was in the sequences, so it's basically the same kind of concept. We've seen, I'm pretty sure everybody has seen the summation symbol before, so that shouldn't be anything unusual. If it goes to a specific number, we call that number S. That's the sum of the series, and that would mean it's convergent. So if it converges, it has a number it goes to. It does not have to necessarily be 0. It doesn't necessarily be 1. It can be any number at all. It just cannot be infinity. So if it goes to infinity, it's considered to be divergent. If it jumps between values, it's considered to be divergent. And everything after this point we're going to talk about is how to determine if it's convergent or divergent. All right, so let's look at this one. We want to see if this series is convergent, and if it is, we want to be able to find its sum. So some of the problems that we're going to look at, we will find their sums. Some of them we are not going to. All right, so when we were looking at the original problem back here, we said if it's convergent, it's got to go to a specific value. So let's actually look at some of the values for this one and see what kind of happens with it. Wrong screen. That screen. So if I started looking at these numbers, 1 is going to be 1 over 2. So this is 1 over 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5, and so on and so forth. So 1 times 2. And it keeps going. That's nice, but not very helpful because it's not really breaking things down. So let's see if we could actually take this and do what we did back in chapter 7 and take this fraction and break it up. So we have 1 over n plus 1. I want to break this into 2 fractions. So my denominators would be n and n plus 1. How did we do this back in chapter 7? Yeah, so we had what? A and B up top, right? Okay, so I had a times n plus 1 plus b times n, and that all has to equal 1, right? So if I make n 0, which will clean that one up, a has to equal 1, right? That was n is 0. And if I make n negative 1, I get negative b equals 1, so b equals negative 1. Correct? Remember doing that vaguely? Okay. So I now have a new summation. I now have 1 over n minus 1 over n plus 1. So I took this right here and changed it to that by using the same thing we used in chapter 7. We were doing partial fractions. We were splitting them up. We basically did the same thing to split it up. All right. So let's look at what this is going to give me as I keep going. So the first one would be 1 minus 1/2. That's the first one, correct? The second one is going to be 1/2 minus 1/3. The next one's going to be 1/3 minus 1/4. Noticing a pattern here? I have negative 1/2 and positive 1/2. They're going to cancel each other out. I have negative 1/3 and positive 1/3. They're going to cancel each other out, right? So in essence, I'm going to end up with 1 minus whatever the last term was, right? Which in this case would be 1 over n plus 1. Because whatever ends up going to be. What's that as n goes to infinity? 1 over, that's going to go to 0, right? Because the bottom's going to get infinitely large, correct? So this sum goes to 1. So it's convergent, and it goes to 1. So sometimes we just work through the problem and see what happens. Not always going to be the easiest way to do it. Some ways that's probably going to be the hardest way to do it. But that is a way to do it. All right. So there's 2 types of series that you learned about at one point: arithmetic series and geometric series. We talked briefly about a geometric series when we were talking about the sequences, and we said that if the R was less than 1, so basically between negative 1 and 1, it was convergent. And if R was greater than or equal to 1, or on the opposite side, to the absolute value of R is greater than or equal to 1, it's divergent. That's important because that gives me an answer. Okay, so if I have a geometric series, I can go Okay, I look at it, the R is here, I know it's convergent. Or the R is here, I know it's divergent. And that would be an acceptable way to tell me if it's convergent or divergent. The geometric series also has the added benefit, if it is convergent, there is an actual value for it. The equation is just A over 1 minus R. That will always give you what it converges to. That's the sum of those values. So in essence, this is our first real test to be able to show if something's convergent or not, is the geometric series. So, and the key piece is these. If it's convergent, if R is, the absolute value of R is less than 1, and it's divergent if the absolute value of R is greater than or equal to 1. The part is going to be figuring out that it is a geometric series, and if it's a geometric series, what the R is. Those are the two pieces of information we need to find to be able to show this. And that's what we're going to look at now. All right, so let's look at this one. It says it's a geometric series, but we're going to figure that part out too. All right, so here's my series. So the first step is, in this problem, I need to somehow come up with what the actual equation is for it. So we always start at n equals 1 to infinity. So it's telling me it's a geometric series, but let's actually try to figure that out from the problem, because sometimes it's not going to show you that. It's not going to tell you that. You're just going to have to be able to figure it out. So my first term is 5. So we'll say A is 5. A is my first term. And then it goes to 10 over 3. So what am I multiplying, or what's changing from each of these basically? Is it something added to it, or is it something multiplied to it? It's multiplied. So if it's multiplied, we're looking at geometric series. All right, so what's multiplied to that number to get to the next one? And that's going to be my R. So it's going to be negative, right? Because the sign keeps switching. So it's going to be negative. Okay. And now we got the top and the bottom, right? So what's multiplied? The bottom seems really easy. It's divided by 3, divided by 3, divided by 3. So it's being multiplied by the 3's on the bottom, right? And then it's multiplying by 2 on the top, right? So yeah, the negative I put in front. So my R is going to be negative 2/3. So I've got 5 times negative 2/3 to the n minus 1. So remember, for a geometric series, you want your problem to look like AR to the n minus 1. That's what you want it set up as. So that's my geometric series for that. So now that we have our geometric series, is it convergent or divergent? It's convergent. Why is it convergent? So the absolute value of R is less than 1, because that's the absolute value of negative 2/3. All right. Since it's a geometric series and it's convergent, we can find what it converges to. So this equals a over n minus 1 minus a over 1 minus r. So that's going to be 5 over 1 minus negative 2/3. So I get 5 over 1 plus 2/3 is 5/3. So 3. So converges to 3. So the sum of this geometric series, no matter how far you go out, it's going to 3. So if you go all the way to infinity, the answer is 3. Yeah. All right. Does that make sense? For the easy one. Now we'll get to the hard one. So they give you this series. Is it convergent or divergent? If you look at it, what does it look like? Yes, it looks like a mess. What kind of series does it look like, though? It's kind of got that multiplication going on in there, right? And whenever we kind of get the multiplication, you want to kind of think towards that geometric series. All right, but it's got multiple numbers, it's got multiple exponents. The exponents are all in terms of n, which is helpful. But it's definitely got multiple things going on up there. So we need to somehow look and see if I can get this to change into the problem that looks like this. I want it to look like that. This is where algebra comes into play. We have to be able to manipulate the exponents to be able to solve this and to simplify it. So let's look at each piece individually. So I have 2 to the 2n. That I can change to 2 to the n, or sorry, 2 squared to the n. Those mean the same thing. Remember, when we're multiplying exponents, it's exponent raised to an exponent. We just multiplied the exponents. So that means that is really just 4 to the n. Okay. If I wanted to make that 4 to the n minus 1, we could have 4 to the n divided by 4. Sorry. I want to write this a little different. Because I don't want to change the problem. So by doing this, I'm not changing the problem. So I have now 4 times 4 to the n over 4, which is 4 times 4 to the n minus 1. All right. So that's 1. Everybody understands how I got 4 to the n? I multiplied it by 1, correct? 4 over 4 is 1, so that didn't change. I used 4 on purpose because I want 4s. So if this was 3 to the n, I would have used 3s. So I have 4 over 4. So I want this. Remember, the whole goal is to get it to be the n minus 1, right? So the only way to get a minus 1 is to divide it, because it's subtraction when you have it on top and the bottom. So this is 4 to the n over 4 to the 1. So that's n minus 1. And then that 4 just stays there. Okay. The other way to look at it is that's 4 to the 1, right? If I'm multiplying like bases, I add their exponents, correct? So n minus 1 plus 1 is just n. Okay. So, all right. So I've got my 2n kind of solved. So 2n now goes to, or 2 to the 2n is now 4 times 4 to the n minus 1. Okay. Now, let's play with that 3 to the 1 minus n. All right. So this right here is 3 over 3 to the n, correct? Okay. If I flip this over, that's really not going to help me. How do I want to do this one? Oh, actually, never mind. I'm going to do it a different way. That's the same thing, correct? That's a better way to look at this one. I think that'll be a little more sense for you. So I can just basically pull out a negative sign, which means that this now is 1 over 3 to the n minus 1, correct? Because the negative exponent just goes to the bottom. Yes? Okay. So pull out the negative sign, move it to the bottom. All right, so now I've taken my 3 to the 1 minus n, and I've now changed it to 1 over 3 to the n minus 1. Notice, the goal is to get my exponents to be n minus 1. Right? Because now the nice thing is the next step is going to make it all come together. We good with this part, Scott? You got it written down. We're going to go with that direction. Yeah. Okay.
You said the goal was to get it to AR n minus 1?
Yes, the goal is to get it to look like that. So we want the main piece is if we can get all of our exponents to the n minus 1, I'm going to be able to magically put everything together in a second. All right, so I have 4 times 4n minus 1 over 3n minus 1. Correct? Okay. Which now becomes that. So the 4 stays out in front because we didn't do it. There's no exponents in that one. Since the other two both have exponents as n minus 1, I can basically pull it outside and put it above a parenthesis. I'm basically doing the opposite of the distribution rule you typically learned when you did exponents. And now it's in my format of a times r to the n minus 1. So is this function convergent or not divergent? What's the r? R is 4/3, which is greater than 1. Therefore, this problem is divergent.
I wasn't looking at the actual number, it was just all fraction.
That's part. So that's the thing. Yes, that is the thing you're going to have to not automatically do, because a lot of times people look at fraction. Oh, it's a fraction. It's got to be less than what? No. So definitely look at your fractions. A lot of these do come out to be fractions. So. All right, let's do one more of those before I do the word problem one. There we go. This one. Yeah, let's do that. All right. Remember our goal. Goal is to get this to a r to the n minus 1. So look at each piece individually and try to get it to that. If it doesn't have an n on it, it's just like the 4. We can just leave it out in front. So like that's 6. Don't play with the 6 right now. Just keep that one out in front. You're really dealing with the 2 to the 2n minus 1 and the 3 to the n. Those are the two things that you're really worrying about right now. %90 of everything you're going to do in this one is being able to manipulate a series to your will. Understand fine for something with a ladder because that would be nuts. So that 3n, right? Yeah. Exactly the same thing. Yeah. And then my suggestion for the 2 to the 2n minus 1, I'd split it. Okay. And then it's going to look very similar. Gotcha. Yes. Split up. Split this. And then we're coming to use. Yep, you can do the same thing. My suggestion would be, if you notice, you go down here, look what it came like. It was just before cut. So don't, we don't necessarily do the steps. You do it right away. So it's 3.
And
No, so because there's not a 2 on this one, you can't do that. Split this up. All right, most that I saw. What's up, Scott?
I know, doesn't say what it is.
Oh, I can come back in a second. I was just gonna do the bottom part. So the 3N, most people kind of got the fact that it kind of works with the same thing with the 4. So that would be your bottom part. The key isn't going to be working with that 2, the 2n minus 1. My suggestion would be break it apart. Start with that. That's still 2.
That's different.
Oh, you can do that.
Okay.
So this right there. This 2 to the 2n. Times 2 to the negative. No multiplication is that. Now, work any two of those.
Gotcha. All right.
That's what, so use the exponent rules to split. So I'm writing the second part of the Calc 2 or planning the Calc 2 book, and my first unit is all review, and it's exponent rules, systems of equations, and long division. It's all the algebra skills that you need for Calc 2. So I'm like, I'm just going to put this in the beginning of the book. All right, so we've got my bottom part. So 3 times 3 to the n minus 1. So we got that to the n minus 1. Okay. We still have the 6 up there. So we've got 2 2n minus 1. That becomes 2 to the 2n over 2. Okay. Now this 2 to the 2n, I basically already did over here. So I'm not going to have to redo all those steps, but that's how you would do the 2 to the 2n. You pull out the 2, make it a 4, so it's 4 to the n, and then we're going to do it the exact same way. So this becomes 4 to the n, and I can ignore that 2 for a second, which is going to be done the exact same way as I just did the 3 to the n. It'll be 4 times 4n minus 1. So now my problem, I now have times 4 to the n minus 1, and I have a times 2 down the bottom. So now let's clean all this up. I have 24 divided by 6, which is 4. That's taking those, that, and becomes the 4. Anything without an exponent, basically, we put together. Those are all, that's going to be my initial number. That's the A. Yep. And then I'm going to take these two, which are both raised to the same power, and get me 4/3 to the n minus 1. And miraculously, it's basically the exact same thing. And I totally didn't even see the answer for this one. The funny part about it is it's exactly the same thing. They didn't look the same. Okay, so the real key to these is understanding those exponent rules so you can manipulate that problem and get it to the way you want it to. Yes.
So originally, why A, I did something. It just inputted for
Yeah.
I still got 4. Is that like a good way, or is like
That's a great way to check afterwards. So one of the ways you can do this is you actually can just do out the first few values and see if you could figure it out. Most of the time that'll work. I like plugging in the one. It just gives you a good way to check and make sure you got it right. And then you can either plug a couple other ones in and see if they come out to be the same at the end. because your goal is you still need to find the R, and that's normally the harder part to find. So, but yeah, that's a great way to check your work and make sure that at least that if that's right, then odds are your other part's right, because if that's wrong, if you got that wrong, then you probably made a bigger mistake somewhere else. So, good way to check your work. All right, let's do a word problem. All right. So I actually think I mentioned this problem briefly at one other point when I was talking about problems. When your doctor tells you to take medicine, take your medicine as prescribed. And this is why. So drug is administered to patient at the same time every day. Suppose the concentration of the drug is CN. After the injection on the nth day, before the injection on the next day, only 30% of the drug remains in your bloodstream. And the daily dose raises the concentration by 0.2 milligrams per milliliter. The concept, like the actual units and stuff like that, don't matter too much. The key piece to this is that after one day, the drug's still in your system. It's not completely out of your system. So if any of you have ever taken any medication that the doctor, like you have to take all the time, if you stop taking it for a couple days, you're going to start to feel effects of it drastically really quickly, because the doctor actually is getting you to a dose that's higher than the actual dose in the prescription bottle. So in this case, the prescription's for 0.2 milligrams per milliliter. The question is how much is actually in the person's bloodstream? Because that's the actual medication level that the doctor wants you at. So if that's the case, then this has got to converge to a specific value. Let's find that value. All right, so step one, let's do a couple. Let's see what's happening with the first couple. So on day one, or yeah, so C1, how much drug do I have in my system? I just got stabbed, right? So I literally have that. Okay, that makes sense? Day two, I have my new injection plus 0.3 of my original injection. So I have 0.26. Now in my bloodstream. Day three, I have 0.2 my new injection. And now I have 0.3 of my original. So that was that 0.2 times 0.2. Sorry. Now let's do it the other way. It's easier to write that way. Of the 0.26. It's easier to write it that way. So this becomes 0.278. Okay. So after 3 days, my dosage, the actual medication in my system is 2.78 or 0.278. It's higher than the 0.2. So the question is, so now are we multiplying by something or are we adding by something every day? So we kind of got to figure out how we're going to actually work this. So let's see if I can somehow come up with a geometric series or something that we can work with. Obviously, if I'm doing this now, there's got to be some way to come up with a geometric series for this. So if I looked at my nth dose, actually, I'm going to rewrite this a little bit. So this part right here, that part right there, is the same thing as 0.2 plus 0.3 times 0.2, correct? So that's basically that piece pulled out. So I could write that step as 0.2 and then 1 plus, because I can pull out the, because there's 0.2 plus that piece. So how am I going to write this one? A 1 minus. Hold on a second. All right, so I've got 0.2 plus that. So if I wanted to pull out, so that's 0.2 plus, oh, that was all times 0.3, that's why. That's the piece that I was missing. I was missing that part right there. So if I distribute this piece through, it becomes a little 0.06 plus 0.3 squared times 0.2. So we can start to see that this piece right here, that's going up. Okay. If we do this out far enough, you get, and I'm just going to copy this one because I don't feel like we're ready. The nth dose is this. Because it's my initial dose plus the piece from every other day. That's there. So that's from the previous day, that's from 2 days prior, that's from 3 days prior, all the way back to the very first day that I got my dose. Yes? Yeah. So if we wanted to take this and rewrite this in terms of a geometric series, we have it's that part right there. Okay. So we've got the A and we've got the R. But that's not going to, that's basically going to end up going to 0. So when we change this, and we're going to do the 1 minus. So remember your what's it called? Growth and decay problems. Your like compounding interest problems. So we have the 1 minus the 0.03. So this is my drop off every day. So if we change this a little bit more, so we're going to change this to 1 minus 0.3 to the n over 1 minus 0.3. I'm going to get my, because the key is remember, R has to be just a single number. In this case, it's not. So it's not going to be very helpful for me to solve in the terms of my geometric sequence. But this part comes out to be this. So I got 2 7s times 1 minus 0.3 to the n. What happens is that goes to infinity. That's basically going to become nothing. So this drug goes to 2 7s in your bloodstream. Which is 2.86 milligrams left over in your bloodstream.
What's the R value?
It's not your R value because it's not a specific geometric series. So the key is you actually have to look at these as separate pieces. So like that part's going to go to 0, that part's going to 1. It's you can't necessarily look at this as just a specific geometric series because it's not doesn't fit that mold. It's close, but it doesn't exactly fit the mold.
That be the same as looking at it as like 0.70 to the nth power. Because the way I kind of do shortcuts in my head is if it's anything less than 1.
Yeah, it's going to go.
goes to 0.
Yeah. Because it's not truly a fully geometric series. That's the case. It's not because remember it's not just R.
But like, so for the big K part,
Oh, wait.
it-
I put my parenthesis in the wrong spot. It's there. That makes a difference in your question. There. Because that's going to 1. That was one little error in my parenthesis. So this goes to 0. That goes to 1. So it's 2 7 times 1. I'm like, wait,
oh, so
multiplies.
you just factored out all.
Yeah.
Okay, that's. So then the like as n goes to 1.
Because that's the 0.3 goes to 0. So it's just because remember limits you can break up and do the limit of each piece. So this is like if you had taken your drug an hour later every day. So there was now instead of 24 hours between it was 25 hours between it. You're not going to have that 0.3 left over in your bloodstream. So you're never actually getting the official dose that the doctor wanted. Now, none of your doctors actually do this out. They have books that tell them, like, or tables and stuff like that, or a computer system that'll say, here's the dose, this is what they actually want the effects to be. So they don't do this out by hand. But the drug manufacturers have to.
So for when you pull out 1 minus 0 point, is there also parentheses around the 1 minus 0 point?
But it's just, yeah, but there's nothing left over it. So I just put it down the bottom.
How did you get from the exponent of n minus 1 to just 10? If it's only the 0.3 that has the n.
It's, no, you're not. But it does go down that way. It's a factoring thing that I just didn't actually do. It's a factoring thing in this problem up here. Because remember, you still have all these other terms that go with it.
Oh,
This, okay, so this piece right here, they look the same, but that -1 did not give me that.
is why it's also a 1 minus 0. So
Okay, hold on. I'll tell you afterwards. Because I'm not going to confuse everybody else. I will tell you afterwards. All right. Yeah, this one. Because I want a few other things I have to get through tonight. All right. What was the one thing I told you last week that that has to be true? Remember last week I said one of the first things that we have to determine, if the sequence goes to 0, then it can, like if the sequence doesn't go to 0, it's divergent, right? So if the series is convergent, then the limit of the sequence goes to 0. Okay, so if the series is convergent, then the limit of the sequence goes to 0. That's worded very specifically. Okay. It does not say if the sequence limit goes to 0, then it's divergent. Then it's convergent. Okay, it's not, the opposite is not true. Always. So if the series is convergent, then I know the limit has to go to 0. That helps. And actually, I'm going to swap these two. I'm going to do this one first. Because of this. This is the first test. Well, the second one, because we just did the geometric series one. If the limit of the sequence does not exist or does not go to 0, then the series is divergent. So this basically is the converse of what the original statement was. Okay? It's not the inverse, not the opposite, the converse. So it's if the limit doesn't exist or doesn't go to 0, so basically if the limit doesn't go to anything other than 0, I know my series is divergent. That was why I said really practice 11-1, because if you can tell that the series doesn't go to 0, you're done. You've passed the test for, you know it's divergent. You don't have to do anything else. Okay? If it goes to 0, it could be convergent or divergent. We don't know. Okay? And that's the problem I'm going to show you in a second. This series is very special. This is known as the harmonic series. So what's the sequence here? This part is just 1 over n, right? And if I take the limit of that as n goes to infinity, what do I get? That goes to 0, correct? We've done that. Okay. If you keep adding, so remember what I said, it's like if the last number is not 0, then it's going to keep diverging because I'm adding more to it. But in this case, if I do 1 plus 1/2 plus 1/3 plus 1/4, that number is getting smaller and smaller. Theoretically, that should converge, right? It should be getting closer and closer to a number, right? That like realistically, that makes sense. It doesn't. So if I was to take the first two, so 1 plus, so S2, 1 plus 1/2, I get 3/2, correct? If I took the fourth one, I get 1 plus 1/2 plus 1/3 plus 1/4, right? What's that equal? Somebody use Desmos really quickly or a calculator. 1/2 plus 1/3. 1 plus 1/2 plus 1/3 plus 1/4 is what? Okay, good. 25/12. Perfect. All right. Remember that whole squeeze theorem we did? This is similar to that. So this ends up being 25/12, right? We just got it. Is that bigger or less than 2? Bigger than 2. Good. If I change this 1/3 to 1/4, this is greater than this, correct? Yes? Because I just made one of the numbers smaller. We're not trying to make them equal. So unlike the other problems, we're changing problems to try to keep it the same, we're not. I'm literally saying that this is bigger than this. So I know that this is bigger than 2. Right? I might not know the exact number, but I know it's bigger than 2. Okay. That's important. Everybody understand what they did there? Okay. Let's take the next one. All right. So if we look at the eighth one, that's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8, right? That'd be all that, correct? Okay. That is bigger than that, correct? And that is bigger than that, correct? Okay. So that means that S of 8, the eighth term, is greater than 1 plus 3/2, so greater than 5/2. I know it's bigger than it. I don't know exactly what it goes to, but I know it's bigger. Okay? So I've now, every time I've added more, the number is getting bigger, right? Okay. All right. Erase this. We're going to go bigger. If I did the 16th one, it's still getting bigger. So 16th is going to be bigger than 3. Again, don't know the exact number, but I know it's bigger than 3. The key with this is that it just keeps getting bigger, right? If it's converging, it's got to get closer and closer and closer to something. But this ends up continuing. And if we did this, the 32nd one and the 64th one, you can see it's getting, again, bigger and bigger. Yes, we're spreading them out further. So this is almost like a logarithmic scale, right? The space between them is getting bigger because we're going up by powers of 2. All right, but it isn't slowing down. So like a logarithmic scale for earthquakes and stuff like that, or hurricanes and anything like that, it always is getting bigger, right? Even though it's kind of like leveling off, it never actually completely levels off. And that's what's happening here. So this one actually ends up going to because we can figure out, if you looked at it, it's basically whatever it is to the n over 2. So if I did 2 to the 10th power, it's going to be greater than 1 plus or 6. If I did 2 to the 10th power terms, it's going to be greater than 6. Okay? So since it never actually goes to a specific value, the harmonic series actually diverges. Okay? So the sum of 1 over n diverges. All right, let's look at this one. All right, show how this one, it says diverges, but why does it diverge? So right now you only have, in essence, 2 tests. You really only have 2 tests right now to show, right? We know geometric series, and we know the test for divergence. That's really all we have right now. So, or you can literally sit there and do it out like we did the very first problem. Is this a geometric series? No. Geometric series are always raised to the n power. So this is not a geometric series. So look at it as a sequence and see if the sequence goes to 0. And then we can use the test for divergence. If the sequence doesn't go to 0, it fails the test for divergence. So I know it diverges. So if I have n squared over 5n squared plus 4, I'm looking for the limit as n goes to infinity. So I'm dividing the whole problem by n squared. So I get 1 over 5 plus 4 over n squared, which goes to 1/5, which is not 0. So it diverges. Yep. If it goes to 0, we have to do something else. If it doesn't, it's done. That was why I was saying, that's why 11th one was so important and why I spent so much time on it. Because if you can figure out that a sequence goes to 0, if it doesn't go to 0, you're great. You're done. Good. that sequence converges. It converges to 1/5. But since it doesn't converge to 0, the series diverges. All right, so we've got, so far, this is what you know. We know the test for divergence. So if the limit as n goes to infinity of a to the an does not equal 0, the summation of an diverges. And we have the geometric series. If the absolute value of r is less than 1, it converges. If the absolute value of r is greater than or equal to 1, it diverges. So those are the two tests that we have currently. There's more. Those are the two we have right now. All right. If two series are convergent, I can multiply that series by any constant and it's still convergent. I can add those two series and they're still convergent. I can subtract the two series and it's still convergent. Okay? If they're both convergent. That's helpful because that means that I can kind of break things apart and figure out if the other series is convergent that I'm going to look at. So let's look at this one. So I've got the sum of 3 over n plus 1 plus 1 over 2 to the n. These two things should look familiar. So it's saying they're convergent because it's asking for the sum, but let's actually show that they're convergent first. So this piece right here, does that look familiar? That was one of the first problems we did. What did the first problem we did go to? What did 1 over n plus 1 go to? It was the very first problem we did. It's literally the first problem we did. 1. That's okay. So it converges to 1. So this, because there was a 3 in front, is going to converge to 3. Because that went to 1, so 3 times 1 is, so it's 3. Now let's look at the 1 over 2 to the n. Does that look like a geometric series? Yes, except it's to the nth power and on the bottom. So let's modify this a little. Let's change this to 1 over 2 to the nth power. Nope, just n. Because it's 1 to the n and 2 to the n. I just pulled it out. All right, how do I get it to be n minus 1? Because I really want it to be n minus 1. What did I do when I had 3 to the n? How did I get it to be n minus 1? Yeah, it's basically, it was 3 times 3 to the n minus 1, right? So this one is going to be 1/2 times 1/2 to the n minus 1. So what's my r? My r is 1/2, right? Which is less than 1. So it converges. So good there. What does it converge to? It was a over 1 minus r. So it's 1/2 over 1 minus 1/2. So that goes to 1. So my original problem goes to 3 plus 1, which is since they're both convergent, we can split them up. Yeah, I'll save that one for next time. All right, I'm gonna actually call it there. So all we did was actually 11.2. Because I don't have time to go into the integral rule right now. So practice 11.2.
Yeah, specific numbers that you suggest, or
I'd start with the odd ones. I'd start with the odd ones. It's just a variety of them, really. Let's see. I would look at 23 through 32. Those are your geometric series. And then the ones after that one gives you a little more of a variety. So yeah, 23 through 50, basically. Yeah. Those are the ones I'd focus on. All right. Okay. 11.2. And I will see you on Thursday.